Good evening, guys. Am I audible? Okay, we can start the class, right? Yeah, thank you. So, in previous class, we learned about decoder, encoder, and demux multiplexer, right? So, yesterday I did give you some tasks, right, to complete that time scale 1ns, 1us. Have you guys completed with that? Guys, in the chat, I need answer. Yeah, okay. I will explain that concepts, okay? So today we are going to learn a new concept called comparator. Have you know anything about comparator? Yeah, okay. Then I can continue, right? So what do you know about comparator? Do you guys have any ideas? Bye, guys. Be fast. So okay, look, I'm going to explain about comparator. Okay. So comparator, it is nothing but it is a digital circuit. Okay. So as we have learnt mux, demux, encoder, decoder, and priority encoder, like that only, comparator is also a digital circuit. Okay. So what does it does? The main thing of comparator is used to compare two binary numbers. Okay. So like in previous classes, I explained about some encoder and decoder producing binary inputs and taking binary inputs, right? Like how encoder is going to produce binary inputs and how decoder is going to take binary inputs, right? So like that only, the main thing of comparator is to compare to binary values. So how does it compares? Okay, so basically in comparator we have 1 bit, 2 bit, and 4 bit comparators. Based on that, we are going to compare the things. Okay, so for comparing we need to know about binary numbers. Okay, like zeros and ones. Based on that only we are going to compare the things. So okay, while comparing, inside the comparator, it tells like how does that particular input is greater than the other input, or else how does how the other input is lower than the other input. Okay, so and it also checks for whether they are equal or not. So like uh, for comparator to think generally, we need to like know some real life analogies. Okay, so think whether like you and your friends got attended some exams. Okay, so your friend got 85 marks and you got around 90 something. Okay, then you will compare, right? Yeah, my marks is better than him or her, right? So like that only, comparator is going to compare the binary values of two values. Okay, so and in the main thing of comparator is to check that comparison. Okay, like higher, greater, or equal, and based on that it will give the result. So look here. This is what the block diagram of comparator looks like. Think A is greater than B, then it will be greater output. Okay, and A is lesser than B, less output. A equals to B, equal output. Okay, so you know some logical conditions, right? So relation, like relation operators or conditional operators, the same conditional operators is going to be operated inside that comparator. Okay, see, and this will be like a somewhat block diagram that relates the comparator. Okay, if A is greater than B, then the output goes to here, the red line what you are looking. Or else if A is less than B, then it choose yellow line. Okay, and if A equals to B, then it choose green line. Okay, so inside comparators, like it doesn't look like this. Just for a reference for you guys, I have given some colors. Okay, so don't confuse that colors. Inside that comparator, we have colors like that. Okay. Yeah, this what I gave some examples, right? Like 87, and 85, and 72. Like this only the comparators works, and also like mobile price example. Okay. So to understand the better way of the comparison, we need to like look into this kind of examples. Okay. Yeah, and there are some types of comparators, mainly like 1-bit comparator, 2-bit comparator, and 4-bit comparator. So okay, what is the difference of this 1-bit, 2-bit, and 4-bit? Okay, so in 1-bit comparator, it compares single bits. Okay, like either A will be 0 or B will be 0, or A will be 1 or B will be 1. Okay, so it just compares that 1-bit input of both A and B. Okay, then it will produce the output. Whereas when you come to the 2-bit comparator, it compares the 2-bit. Okay, so this uses MSB priority. It like while studying priority encoder, you got the point about priority, right? So MSB means most significant bit. Okay, so I will explain once. I will go into 2-bit comparator deeply. Okay, so in 4-bit comparator, we are going to compare 4 bits. Okay, yeah. Look, next we are going to study about 1-bit comparator. Okay, so as I said, it compares 1 bit that will be either A will be 0 or 1, or B will be 0 or 1. Okay, this is what the 1-bit comparator is going to do. Like it compares the 1-bit value of A and B. How it works? Compare single bit inputs A and B. If A and like what I said, if A is equal to 1 and B is equal to 0, greater input is I, right? So what will be the output here? A, right? Why? Because A is on state. Okay, it means true condition. Okay, when you come to the second case, if A is equal to 0 and B is equal to 1, okay, here what happens? B will win, right? Why? Because B is in the on state. Okay, like that only. If A is equal to B means A also will be 0 and B will be equal to 0, like that. Okay, so equal outputs is I. Okay, so like this, how it works in the inside the 1-bit comparator, and this is what the truth table looks like. Like when A and B are both are 0, then what are you going to get? Here A and B are equal, right? So what is the case operates here? Third case, right? Where A is equal to B, case will be operated here because both values are 0. So you will get A is equal to B as I. And for the next condition, 0 1. Okay, so here B is in on state, means A is lesser than B. The second state will be in like I, right? That B condition is in I, so the second case works here. So you are going to give an I state to A is less than B. For next condition, A is I, right? So we will give I state to A is greater than B. Why? Because A wins here. For last condition, we have both A and B is equal to 1. So when you have both A and B is equal to 1, both are equal, right? So which condition applies here? Guys, can you mention the case in the chat so I can know that you are guys listening to the class? So which case will work for when both A and B is equal to 1? Yeah, third case, right? Then what happens? Then A is equal to B case will gets I, right? So this is what how you are going to understand like truth table of this simple one bit comparator. Okay. So how to write Boolean equations? Okay. Like after learning truth table, the main thing to know about the truth table is to get handy with writing Boolean equations, right? So how are you going to write Boolean equation? Look here. Here we have something like A is equal to B, right? A is less than B and A is greater than B, right? So you can name this A is equal to B as equal, A is less than B as lesser, and A is greater than B as greater. Okay. So how you are going to write? If you like solve this case, you need to get that answer. Okay. So for A is equal to B, this is what somewhat looks like one truth table, right? Like uh, there is one gate, right, where when your both input is same, then you are going to get one, right, or else zero, right, which is the truth table. Can you mention that? If both value is same, then we are going to get output, right, which is the truth table, like which is the gate that defines this truth table? Guys, I need answer. Guys, which is that gate that will give output only when the two input are equal? XOR XOR AND gate. I'm asking that if both A and B are equal, then we will get the output as 1, right? So this condition is satisfied by which gate? Okay, I got some of the XNOR, right? So the right answer is XNOR, okay? So this XOR and are wrong. Why? Because XOR is the opposite of OR gate, and AND gate is going to provide only if both the inputs values are 1, okay? So don't confuse with that. AND gate is going to implies when both A and B are in on state. Okay, so XR is like its truth table is like 1000, means it's going to imply when both A and B are 0. Okay, so the right answer is XNOR. Inside XNOR, if both A and B values are same, then only we are going to get output. Just remember, don't forget the gates because you are from VLSA background, right? So electronics background. So if you forgot about gate, means there is no use of studying verilog. So okay, coming back to the Boolean expression, okay. See here, how to write the Boolean equation. What does that XOR do here? XOR means it works when only when the both values are high, right? It opposite of or, right? So give the answer here, okay? So A will be 0, B will be 0. XOR will produce 1, right? So how this works here? So what is the truth table of XOR? Truth table of XOR is 0, 1, 1, right? 0, 1, 1, 0. So if both values A and B are 0, 0, okay, what happens for the first condition? So it's truth table, XOR truth table tells that if both the values are 0, 0, so it's going to produce 0, okay? So XOR only works when the both input values are changing, okay? So XOR doesn't work for the uh, for when both values are same, okay? So XOR is usually basically it's opposite of XNOR, okay? So don't confuse NOR with XOR. So what will be the truth table of XNOR? What will be the truth table of XNOR? How it works? It's going to work, yeah, 1001, yeah. Basically the XNOR is going to work when you have both inputs same. So XOR will be opposite. It works when you have different inputs like 10 or 01, okay? So if you apply that condition to the Boolean equation, first what we have in truth table, we have 00, right? So if you apply 00 means what will be the output of this A and B XOR? It's going to produce 1, right? Sorry, 0, right? Because both values are same. So if 0 means not of 0 is going to be 1, right? So you will get equal is equal to 1. So that what you are getting here, okay? Like that only how it works, okay? So you need to know this Boolean equation to write from the truth table. If you learn how to write this Boolean equation from the truth table means the gate level implementation will become easier, and you will get to know that, oh, this compare one bit comparator is going to use this much of gate, okay? So how many gates are totally used here? And not one, two, three, four, five, six, right? So inside one bit comparator there will be 6 gates, okay? So this is how you are going to calculate the gates. See here, this is what I said, right? How many gates are there? One, two, three, four, five, six, right? So this is how one bit comparator works. I hope everyone got my point, okay? So coming to the verilog code, okay? So this is what the most part where we need to do for learning verilog, right? Verilog and VLSI, okay? So how to write this code? First we need to name the module. Why module? Because module is going to define the design of an hardware block, okay? So what is the hardware block name here? Comparator 1 bit, right? So look here, we have not started that hardware block name with any numbers, right? So basically there is a rule that you can't start that variable with number or any special characters, okay? So after that you need to prescribe that particular hardware block. How you are going to prescribe? You're going to like name the ports. What are the ports that one bit comparator has? Like it has two inputs and three outputs, right? One is greater, lesser, equal, and we have used for like simple verilog code, okay? using assign block. Whereas you can also write this inside a always block using if case, and like case statement, right? So yeah, and after creating a design code, you're going to create a test bench code. Why test bench code? Because we need to simulate that particular design, right? Whether it's working correctly or not, like that, right? So we need test bench code. Okay. So like you have mentioned the test bench code and its output, input, everything, and after that we need to use like create an instantiation between design code and test bench code, right? So how do you going to instantiate that connection between design and test bench using that module name and UUT, right? What is meant by UUT? UUT is nothing but unit under test. So what does it's going to do? It's going to map the ports of design code to the test bench code. Okay, here dot a of a comma dot b of b is nothing but you are porting your test bench ports to design ports. Okay, so after that you are going to use initial begin. Okay, in previous class I said I asked on explained you one case, right? What happens if you write this one of this case after the end? Okay, after the end. Okay, what will happen? Did you guys searched about it, or did you guys checked inside the idea playground? Guys, did you get what I mentioned right now? I think none of them put an effort. Okay, yeah, it won't run, right? Why? Because like it only solve for that particular three cases. Because initial begin, what does that initial begin keyword does? It's going to like it's tell the your code that you need to begin only once. Okay, after beginning what the procedure, what are you going to do, and you will end the procedure. After that you give, yeah, after you give any other test case means now you code like it thinks like, yeah, I have begun my process and I have ended using that end keyword, right? So after that nothing matters. Okay, it will take that case as an like exception. Okay, so then it will only test for that particular three cases and it will end that module. Okay, so I hope one has tried. Okay, so coming back to this verilog code. Okay, so this is how that you are going to create a test bench and verilog code for that one bit comparator. Okay, so this is how the simulation looks like same for if a and b are one. Okay, like a is 0 0, a is 0 and b is 0, then you are going to get equal, right? So you are getting equal here. Okay, if a is 0, b is 1. Okay, so like don't think about these lines. Okay, so just that waveform is at get scrambled. So if a is 0 and b is 1, right? So b is greater, then what is your output will be lesser, right? See, lesser, it's going high, right? Here, yeah, this is what you are going to generate inside a playground using ep wave. Okay, so these everything are going like used inside a cpu ALU. CPU means you guys know about CPU. ALU means arithmetic logical unit. Okay, so where it's inside arithmetic logic unit, like one input is going from coming from like any of the ports, right? Like mux, demux, like that. And inside that arithmetic logical unit, this comparison will happens. Okay, so you can feel this example when you go depth in VLSA. Okay, so in upcoming classes I will teach and I will give examples for that also. Okay, so don't worry about these things for now. So next, after one bit comparator, we are going for multi-bit comparators. Okay, multi-bit comparators is nothing but 2-bit and 4-bit like that. Okay, so why do we need multi-bit comparators? Okay, so before going that, what is the limitation of 1-bit comparators? The limitation, like as the usual that name says, that is only comparing for 1 bit. Okay, so what happens if your machine is getting input from multiple inputs, like how does that encoders work, like priority encoder, right? So there will be multiple inputs will be high at a time. So what happens when you are like that machine or chip will get multiple inputs? So at that time we need multi-bit comparators, right? Like 2-bit or 3-bit, 4-bit, like that, right? So that's why we need multi-bit solution. Okay, so how that comparison works here? Look here. Here we have A input as 10 and B as 01. Okay, so what is the value of this binary numbers 102, right? And 0 for 01 1, right? So 2 is greater than 1, right? Like this, how it's going to work? Okay, based on that binary values. Okay, so this is how the block diagram looks like. Means here A bracket of 1 is to 0 means nothing but A is getting 2 bits value. Okay, so B is also getting here 2 bits value. Okay, this is how that 2-bit comparator looks like. If you understand 1-bit comparator, then it's nothing but inside 2-bit, like one input is getting 2 bits. Okay, like A is getting 101101 or 00 like that, and B is getting same as 1. Okay, so after that, so inside that, there's one concept called as MSB priority logic. Okay, MSB is nothing but most significant bit. Most significant bit means, like, see here. Here we have 10, right? 1 is most significant bit. Okay, and 0 is least significant bit. Okay, so a value which comes to your left side are called as most significant bit, and for the right side of the value is called as left significant bit. Okay, so how to compare that? Okay, first step, we need to compare the MSB of that particular inputs. Okay, so A1 and EB1. Okay, it's greater, and like you need to compare like this. Okay, and after that, comparing the most significant bit, you're going to compare the least significant bit. Okay, so this is how you're going to compare. Look here, this is the comparison flow between the most significant bit and like least significant bit. Okay, now your input A is receiving 10 and B is receiving 01. Okay, so first you need to compare most significant bit, MSB. So what is the MSB of A? 1, right? MSB of B is 0, right? So which is greater? A is greater. So A is greater here, so A wins. Then the obviously the output will be 1. Okay, and after that it compares, like after that it stops. Okay, so now for the second test case, A is equal to 01 versus B is equal to 10. Okay, now we have B as uh, 1 as most significant bit, so B wins. Okay, then stop. Like that, how it's going to work. Now we are A is equal to 11, B is equal to 10. Okay, so here, look here, in first two test cases we got our winner from MSB, right? Because we got in the first case only, like first we need to, what how does the step works? First we need to check for MSB, and after that LSB. Okay, so here we got winner in the MSB only for first case and second case, whereas in third case, look here, A is equal to 1, B is equal to 1. Okay, so here both bits are equal. So then At this time we need to go for LSB. Okay, the program doesn't stop here, it will go for LSB and it checks for LSB. Here LSB, A is equal to 1, B is equal to 0, so A wins, right? So you are going to pass A as an output. Okay, so greater, this is how works. And same for, okay, like if the board, if every bits inside that inputs are equal means obviously you are going to get equal as an higher. Okay, so next with the same, go for like creating a module, 2-bit comparator. Okay, and after writing a model, okay guys, like I'm going to give a task. Just go and produce inside a EDA playground. Okay, so this design code and a test bench code. Okay, for 2-bit comparator. So this is how that looks like, way from you're going to studio. Okay, so if A is 00 and B is 01, what will be the output here? Both MSB are 00, LSB of B is 1, so you're going to get uh, less as 1, right? Because, okay, next 4-bit comparator. Okay, so 4-bit comparators work like that only. Okay, so just practice this 4-bit comparator. Okay, just apply the same concepts like MSB and LSB inside that bit comparator logic, and then create a design code and a test bench code for this 4-bit comparator and run inside the EDA playground, and study that 4-bit comparator using EP wave. Okay, so in previous class, like I said, I did mention something about time scale, right? Like 1 ns per 1 ps, 1 us per 1 ns, right? So did you guys find out the difference between that? Guys, I need answer. Just give me the answer inside the chat. Okay. So like, have you tried checking it once inside a EDA playground? Oh, okay. No answer from the chat. Okay. I think no one has tried. Okay. So look here, I will going to explain that. Okay, inside the EDA playground. I think everyone can see my screen. Okay. So look here. Here, what I have done is I have not created a design and test bench code separately. Okay. In previous classes, oh, we are going to create a design code and then a test bench code, right? Just for explanation, I have created design code and test bench code inside design code only. Okay, so don't just confuse. Okay, and also this is not a good practice. Okay, you need to always create design code separate and test bench code separate. Okay, so just for your understand, like to get the point clear, I have created it separately. Okay, so look here, I have used some time scale, right? 1 us 1 ns, and after that I have created a module encoder, where encoder has four input and two output, right? So I have also assigned what is the operation that's going to done inside an encoder. Okay. After that, I have written test bench code. Okay. So this is how you are going to merge the design code and test bench code. Okay. Inside same code. Okay. So after that, I have given initial begin where it's going to run only once, and I have mentioned the cases. Okay, so like D is equal to 4-bit 0001 is nothing but it's going to assign this D value with this bits code. Okay, what is that? 0001. Then what will become? Then your most significant bit become 0 and the least significant bit will become 1. Okay, then according to this bit code, what will be your d0? D0 will be 1. D 1 is equal to 0, D2 is equal to 0, D3 is equal to 0. Okay, this is how it's going to work. Okay, as I mentioned here, four inputs, right? So this is how it's going to assign if you write like this. Okay, so look here and finish, and I will become like initial begin, and I said to monitor that values. Okay, so look here. First, what we have got here, when you run this code, what is the output you are getting? Time is 0. Why? Because inside monitor, what are you giving the time, starting time 0, right? Percentage 0 t means nothing but you're starting your time from 0. Okay, 0 units. Okay, so that's why you're getting time is equal to 0 for the first condition. Okay, when time is equal to 0, the first condition executes, and after it will wait for 10 units of time. Okay, so you get y, and after that 10 units of time. Okay, 10 units of time, nothing but this. Okay, so after that, second test case will run and give output, and 10 units of time will be added here, and 10 units of the time. At last, you are going to get 10 units because why? First, it's going to start from 0. 10 units, it's become 1000. Next 10 units, it's going to become 2000. For next 10 units, it's going to become 3000. And also, look here, for the fourth condition, you are also given 10 units of time, right? So it will finish with for 40,000. Okay, so look here, what you have inside here, inside the curly brackets, you have 1ns, right? So why you are getting that 1ns? Because you use time unit. Okay, so you are precisely mentioning, okay, 1 us is nothing but like time scale, right? And 1ns is nothing but precision scale. Okay, so you are mentioning that it's going to work inside a precision scale, right? So it obviously it's going to calculate in 1ns. Okay, so this is what the difference. If you don't give this monitor, you can't see the difference between this time. Okay, because basically it's, this is how it's going to work. Okay, if you give like the somewhat time scale means it's going, you will get the units. Okay, like how it's the time is calculating. Okay, just for the calculation of that time in unit, you are going to give time scale. Okay, now we will just change this to 1ns, 1ps. Look here, now we have mentioned to calculate the time scale in precisely in PS. PS is nothing but picometer, right? 1ns is nothing but nanoseconds, picoseconds, whereas 1 us is microseconds, like that, right? So see here, you can't find a difference inside the time because it also started from 0 and keep on adding 10,000, 20,000, 30,000, 40,000. But look here, it is calculated the time in 1 ps. Okay, so this is how the difference between time scale like 1 us, 1 ps, 1ns looks like. Okay, so I hope everyone got this point. So for tomorrow's class, we will start with new concepts. Okay, for this class, this is enough.